Okay. Come on. Okay, so now that we're recording, welcome to Math 721, officially called Mathematics of Scientific Computing 2. So the strange thing is, one time years ago, when I was looking through our course catalog, and I saw a number of courses that we had on the books for all this time that no one was actively teaching. And I noticed two in particular, 720 and 721. And each one of those, Mathematics of Scientific Computing 1 and 2, focused on various aspects of numerical analysis, and in the second one, in particular, dealing with either ODEs or PDEs. And I thought, you know what, that'd be a really cool course to have. Why aren't we running that? And so I wanted to have an interesting course to run during summer of 2017, and thought, you know what, I'm going to dust this one off and run it, and fill it with what I feel like. And I found some materials from a free online course that runs at MIT on numerical methods for PDEs, because also, as you know, we have several faculty here in this department whose research specialty is numerical methods for PDEs. So, you know, myself and Dr. Chen and Dr. Tian and Dr. Zhu, and we focus on different aspects, but that is our area. And maybe to a lesser extent, you know, Dr. Ding or Dr. Xi, and yet we've had no course in that area, and that just seems odd. So I thought this would be a good way to do something about it. And so here we are. And okay, so what I'm going to do is start the old screen share and deal with usual things of getting a course going. All right. Let's make sure I have all my stuff set up. Okay. Come on. All right, let's share a whole screen. Okay. So actually, I'll go to Canvas first. All right, so here we are in Canvas, and as you've seen in other classes I've taught, that I have all the items in Canvas, but I also have the course website hosted on the math department server that's linked here, and that's what we have here. And so as far as what we already have here, the coursework is already here for the whole semester, and I'll come back to that in a moment. Okay, just stuff from the syllabus. So we don't have a textbook per se. You all have, you know, my textbook that's Explorations in Numerical Analysis that's been used in other courses, and chapter 14 in that textbook can be a good reference. That it kind of grew out of things that I did in 721. Now, here we have the grade is decided very simply. So 70% homework, 30% final exam. The homework, there are 7 problems, not 7 assignments, 7 problems. These problems are nasty. So you can see why it only takes 7 of them to fill a semester, because they tend to have multiple parts and so forth. And the final exam will be oral, something that's easy to do in a small class like this. So we would set up a Teams meeting for say a maximum of, say, like, 45 minutes, where I get to ask you about whatever was covered, and that's something we'll handle at the end of the semester. Okay, but there's the other usual syllabus stuff. And here's what I'll be covering. Of course, you know how this group knows how I am about homework deadlines, but I still feel obligated to put them here, at least as a guideline, if nothing else. They're based on whatever point in the semester the corresponding material has been covered. So I tend to put these due dates like short, not too long after that. Notice here I don't have it by the day like I have done in other classes, but it's by the week. Okay, so so whatever notes I have, that's for Tuesday and Thursday. Okay, and then as I mentioned earlier, and I'll be posting whatever notes I have and whatever a link to a recording of a meeting I'll post here also, and all of that will also be posted in Canvas. But you're familiar with that from prior classes. It's all the same. Okay, so these are the assignments, and I have a separate document that has hints that have emerged from common questions I've gotten during previous instances of this class, and those hints will definitely be needed. Okay. Over here, this is something actually I have not posted in Canvas. This document here, these are my notes from a previous time. So I have one PDF that has everything in it. It's like 50-something pages or so. So if you were to download that from here, you'd have everything. Although what I'll be doing is throughout the semester, updating the notes based on what happens in class, like whatever questions I get or things I need to elaborate on. Because admittedly, the first time I taught this class in 2017, these notes were kind of thrown together. But at least you'll have something to go on, and then it'll just keep getting refined. Okay. As I mentioned earlier, this course is based on one of MIT's open courses, and that's this course here. Although I haven't actually tried this link in a while. Let's see if it still works. Yes, it still works. Now this what you're seeing here is just a subset of a material covered here. Now we'll see what happens as far as when things get covered. I may end up covering more if time permits, although in the past it hasn't really worked out that way. Okay, now before I continue, are there any questions about how the course will be run? Okay, quiet bunch as always, but that said, in this case there's not much to it administration-wise. I try to keep it simple. Okay, so now I will flip to the notes. Okay. All right, so I want to give a quick overview. Okay. Of what we're going to see during the semester. So even though this is a course that's nominally about numerical methods for PDEs, I don't get into the numerical methods right away. Certain essential aspects like how we classify PDEs, property solutions are supposed to have for certain fundamental PDEs, well-posedness, what does that mean for PDE to be well-posed, certain PDEs of importance. Certainly, things I'll cover at the beginning, you might find reminiscent of what we see in regular PDE courses here that you've taken, such as 517 or 606. I know at least a couple of you taken that. Okay. So starts out more on the theoretical side, and then I get into finite differences, and then also convergence analysis. What's also covered, actually, we can see that. Okay. Well, everything is here, but also spectral methods. Break down certain categories like Fourier spectral methods if a solution is meant to be periodic, or Chebyshev spectral methods when it is not. Okay. Also, this next part would be somewhat reminiscent of 610, because there are systems of equations to solve for certain methods, like iterative methods for solving Ax equals B, although not necessarily the same iterative methods that were covered in 610. In 610, we saw steepest descent, conjugate gradient. Here we're going to see other iterative methods like stationary iterative methods like Jacobi or Gauss-Seidel, also multi-grid methods, things like that. Okay, and also when you have a time-dependent PDE, like the wave equation or heat equation, you discretize a problem first in space, and that gives you a system of ODEs. So time-stepping methods for ODEs will be of importance. For example, Runge-Kutta methods, multi-step methods, etc. And when you're dealing with time-dependent problems, you have to make sure that your method is stable, that does not accumulate too much error over time. So an important topic will be stability analysis. Okay. All right, so that's a rough summary of what you'll be seeing in this class. So covering a fair amount of territory. Okay. As for the coursework involved, the homework, okay. Most of the homework, like with the exception of the very first problem, is pretty much all MATLAB, or answering questions about how the code behaves, and possibly with some analysis thrown in. But yeah, there's going to be a ton of coding, and because of that, there may be some days where, based on where you're at with the homework, I might choose not to necessarily cover new material that day, but focus more on what's going on in MATLAB. Now, I've and hopefully everything goes well with. And this is meant to be an in-person class, and it's not today. Although I do need to make an announcement to you that per Dr. Schroeder, although I'd said previously that this first week will be virtual, because I did have a COVID scare, but it turned out not to be, thankfully. But Dr. Schroeder insisted that I return to campus as soon as possible. I guess there's this really draconian push from above for in-person teaching in the middle of a surge of a pandemic, but whatever. So I will have to be teaching in person on Thursday, even though I previously said I was going to get that going next week. Now, from your point of view, it's really a matter of choice, because I know that we're returning to fully in-person learning, and I know a number of you are in-person teaching right now, and all of this can be quite stressful with so many COVID cases happening, this just latest surge. And so I want to I'm going to be as flexible as this in-person teaching obsessed administration will allow me to be. And what that means for you is that even when I am required to be teaching in Southern Hall 302 for this class, how you participate in class is up to you. So starting on Thursday, you can either join me in Southern Hall 302, or you can continue to attend virtually. So this Teams meeting I'm conducting right now, I will do that every class. So on all the other days when I'm in the classroom, I will have my laptop there. I'll be pointing the webcam at the board. I'll be running a Teams meeting. It will be recorded and posted. So it's just a matter of whether you see me going through these notes here, like today, or I imagine most of the time running on the board. Fortunately, this class is very small, just 5 people. So it's very easy to be socially distanced in the classroom that holds got the capacity of like over 30. So it's perfectly fine for everybody to be in attendance. But again, it's totally your choice. What I've done in the past with this class is on days where I make it more of a MATLAB day, where we focus more on the homework, just to address difficulties that people are having, because a lot of times everybody in the class might have the same difficulties. Where I've had students work together, like if they want to pair up, which it doesn't work so well here because we have 5, but also that would go against distancing. But really, it's just a matter of how you feel comfortable going about it in terms of how you participate in class. So there may be, evidently there are certain requirements for me, but just as those of you who are teaching have certain requirements to deal with also. But within this class, whatever requirements there are do not extend to you. So actually, I'm kind of curious as to how we'll go as far as how many of you will choose to come to SH 302 and how many will stay virtual. Okay. So no, Chelsea, you don't have to sprint or necessarily make the journey at all, but it's up to you. Okay. Alrighty. So are there any questions at this point?
No, sir.
Okay. Well, alrighty. Let's see. Yeah, I'm not sure why it's different this year, because I mean I've often had times where I teach in fall and spring, and then not during the summer, like not teaching regular classes anyway. And it's perfectly easy when fall rolls around again to just get back into it. But I don't know, it just seems harder this time. But I suppose we can all understand why. Okay, so let's start covering stuff. And we're just going to start with the very basics, even though I know that all of you have dealt with PDEs, but I figure review never hurts. So the problems that we'll be looking at will consist of some partial differential equation that's specified on some domain that I'll refer to as omega. Now, I want to emphasize here that omega, while it would be some subset of Rn, where n is the total number of independent variables you have, those n independent variables could refer to coordinates in space, and they can also refer to time. So, for instance, I could have a problem as defined on an interval in x, and also in in t. So we have one space dimension and also time. So n would be 2 in that case. So the domain, omega, in that case, could be like the whole real number line for x, from minus infinity to infinity, or it could be a bounded domain like x between 0 and 1. Cartesian product with, say, a t greater than 0 for time. But then, to fully specify the problem, we need conditions enforced on the boundary of whatever domain you have. So I'm calling them boundary conditions, but if one of these variables happens to refer to time, then that would be an initial condition. Okay, so I do not have, okay, I do not have an example here, but I will put one in. Okay. 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 So a possible domain in this case might be, say, the interval 0 to 1, Cartesian product with the interval 0 to infinity. Okay. This interval for space, and then this interval for time. So the boundary consists of the endpoints of the interval in x, so 0 and 1, so just those 2 points. And for all time. Okay. All right, and this symbol, okay, so I'm using gamma. Hold on. Okay, so gamma would refer to x is 0, x is 1, and then for all time. For boundary conditions in space. And I'm going to make a set that consists of all of that, all of those points. Union with the domain of a boundary over here. So here we'd have the boundary of this domain would be still all the spatial domain for x, and then the boundary would be t equals 0. Okay, and I'll make that a set. Okay. So to explain my notation here, first set, I always put this set for x first. All right. So, so this part, so boundary conditions are specified for both of these sets. So those are boundary conditions. And then for the boundary in t equals 0, and for all x in the domain under consideration. Initial conditions, but because we're talking about a boundary of this domain, t equals 0 is part of a boundary of this domain. You can think of these also as boundary conditions, all of this. It's just that when it's time, we use the term initial conditions for clarity. Okay. So any problem we're going to work with, we need a PDE, and then we need whatever conditions on the boundary of whatever domain we have. Notice this symbol, you've seen this symbol to refer to partial derivatives, but it's also used to specify boundary. So gamma here is, no, I do not want that. Okay. The boundary of omega is all this. All right. Now, how we specify derivatives, and when you're talking about functions of a single variable, you just think in terms of first derivative, second derivative, etc. But then when you have functions of several variables, then we need ideas from linear algebra to describe derivatives, because derivatives with respect to several variables are involved. So if you have a function u of n variables, then capital Du refers to the derivative of u, which in this case consists of all possible first partial derivatives of u with respect to the n variables. So, this is often called the total derivative, but it's also better known as the gradient. So if a first derivative would be a vector, but then higher order derivatives would be higher dimensional arrays. So for example, if I want all possible second partial derivatives of u with respect to the n variables that you have, then what you would do is arrange them in a matrix. So d squared u refers to the second derivative of u, and so that's a matrix that is described as the Hessian. And the assuming that the second partial derivatives of u are continuous, the partial derivative of u with respect to like x1, x2, or x2, x1 would be equal, and therefore this would be a symmetric matrix. Now, if I wanted to go further, like higher order derivatives still, then those would be higher dimensional arrays. So we have like a three-dimensional tensor would be the third derivative, and so on. But most of the time we only deal with like a first and second derivatives here. But I want to equate you with this notation, capital D referring to like the overall derivative of your function of whatever order. Because this notation is often used to describe like general categories of PDEs. So now I can use that notation to describe PDEs as generally as possible. So what we have here, this equation is the most general PDE that you can have. So you have some function f that defines an equation, and that equation depends on your solution u itself and all of its derivatives, first derivative, second derivative, etc., to a certain order k in this case. But the equation that relates to these things can also depend on x directly. So you could have functions of x, where x refers to all of your spatial variables involved in the equation. So the highest order derivative, a partial derivative that you can have, defines the order of a PDE. So this equation describes a kth order PDE that characterizes your solution in terms of itself and its derivatives up to order k. So the goal is to find your function u so that u and its derivatives up to order k satisfy this equation, and that would be your solution. and we see that your function f depends on as its domain omega, because that's where x comes from, and then u is a real valued function, and then here we have its first derivative, that's a vector, so that would be a vector in Rn, and then these other arguments are higher dimensional arrays, so we have entities that come from r n squared, n cubed, etc., all the way up to r n to the k for a k-th order derivative. Now, so this describes all PDEs, but generally what we like to do is work with certain PDEs of a specific type, because generally solution techniques are meant to apply to certain, whether they're analytical or numerical, are applied to certain categories of PDEs, or applicability might be limited. And so it's important to be aware of how these how PDEs can be classified. For example, PDEs that usually deal with in, for instance, classes like 517 or 606, most of the time are linear. So this would be like the most general linear PDE that you can have. So what we have here is so you can think of, if I were to rearrange this, like this is equal to 0. Okay. Then everything you have here describes your function capital F. So it depends on x through a function little f of x, and it depends on the derivatives of u, but notice that we have here is not an arbitrary function of a derivatives of u. Rather, we have this linear combination that each of these derivatives is multiplied by a function of only x, and that's called a coefficient. Okay. Oops. Dang it. Okay, so these are the coefficients of a PDE. All right. Now, so equations, PDEs that you've seen in other classes, like Laplace's equation, heat equation, wave equation, all of those are linear. Generally, when those PDEs are discussed in those classes, the coefficients that you have here are constants, but that's certainly not required. Even if they depend on x, that would be called a variable coefficient PDE, but still it would still be linear. Okay. Now, I need to explain something else about this notation. All right, I'll do that here. The quantity we have here, alpha, is called a multi-index. So it consists of integers that are meant to be indices. And if we have k indices, then how many indices you have, k, that's what this absolute value refers to. So really, it's not absolute value, but rather cardinality. So that's what this notation means, that we're looking at all multi-indices of okay. Or sorry, how this is defined is just the sum of all the wait, sorry, my memory is foggy on something here. Okay. Sorry, I made a mistake here. I'll just fix this up. The idea is we have a differentiation operator for functions in Rn. So the multi-index actually has to have n elements. The n elements, sorry about my mistake earlier, correspond to the variables that you have. So if u is a function of n variables, we have to have n indices corresponding to x1, x2, up to xn. The magnitude of the multi-index is the sum okay. Wait. Okay, yes. All right. Oh. So this is a convenient way to express all different kinds of partial derivatives that you can take of a function of n variables. Okay. Right. So one of the best known differential operators and I'll work with 3D here. So in 3 dimensions, the Laplacian would be uxx plus uyy plus uzz. So if I want to express this in terms of multi-indices, it'll be a sum of 3 different differentiation operators. So first one would cover second partial with respect to x. So the multi-index there would be 2, 0, 0. So 3 indices total because we have 3 variables, x, y, and z. Here we have the first index being 2 because it's second partial view with respect to x. So then, can anyone tell me what operator I would have next for handling uyy?
D020?
Yes. So again, three indices. And then this would handle z. Okay. Now, each one of these differentiation operators is of order 2. Because the absolute value or magnitude of each of these multi-indices is 2, because if you add up all the indices in each one, you would get 2. Okay. Another example. Okay. Or if I have a function of 2 variables, and I'm taking uxy, it'd be d11. So I have 2 indices, because I only have 2 variables, x and y. I differentiate in respect to each one once. And because the sum of these is 2, that's also a second order differentiation operator. Okay. One more. The beam equation features, and I'll show you that a little later, a fourth derivative with respect to x. D40. So fourth order with respect to x. Okay. It involves 2 variables, x and t. So we have a 4 for x and then a 0 for t, because we don't have a differentiation with respect to t in this part. Okay. All right. So any questions about multi-indices? I apologize for my memory of those being rustier than I thought it was. It occurred to me while I've worked with them before. I haven't. It's been quite a while since I've actually taught about them. All right. So the idea is, if you have a PDE of order k, then you're going to have differentiation operators featuring multi-indices of however many variables you have, where the sum of all the indices in them is at most k. So that's how differentiation is being described in an equation like this. So that's a linear case where the coefficients that you have depend only on x, and any terms that do not include u at all also depend only on x. All right. The next category up is semi-linear. So here, this first part is the same as the first part of the linear PDE, coefficients depending only on x. But now we have this term here. You think of it as like a source term that depends not just on x, but also u and its derivatives up to order k minus 1. So we have here, we can have derivatives of up to order k in this part, but source term cannot have derivatives that are that high. The thing is that, and if time permits at the end of a semester, I'll give you more information about it. I actually have a problem with my research with Naval Research Lab this summer. That was a PDE of order 3, because it had third order derivatives with respect to time. And the PDE fit the definition of a linear PDE like this. But to try to solve it numerically, I actually treated it more like closer to a semi-linear one, except I violated this condition here. But that was just as a perspective that helped me come up with a good method of solving it numerically. Okay. So here is just a small deviation from linear PDE that this source term is more flexible. Here we get a little more flexible still, a PDE that is quasi-linear. This part is the same as in semi-linear case. Here, the coefficients are now allowed to depend on u and its derivatives, again, up to order k minus 1. In other PDE courses where you learned about the method of characteristics, you probably saw that applied to certain nonlinear, really quasi-linear PDEs, such as, for instance, Berger's equation, that I'll illustrate for you a little later, that fit this form. So method of characteristics is when it's often used to solve quasi-linear PDEs. And then if a PDE is not linear or semi-linear or quasi-linear, we just call it fully nonlinear. So those are the nastiest ones of all. Okay. I think it's when we get to specific PDEs, like the ones we'll deal with throughout the rest of the semester, we'll actually move away from this multi-index notation. But for discussions about broad categories of PDEs with any number of spatial dimensions and so forth, this multi-index notation comes in handy. All right. Now, everything I've shown you up to this point involves one equation that's a PDE, but you can certainly have systems of PDEs as well. So what happens in this case, you have a function that depends on the same variables as before, as the inputs. It's just that the output is no longer a scalar. It's a vector in Rm. So M is the number of PDEs in the system. And we have, so U in this case is not just a single function of X, but it's a vector valued function of X with M components. And generally for a system like this to be well posed, if you have M equations, you should have M unknowns. So it's typical for N and M to be equal. All right. And it's quite common practice for instance, PDEs that are higher order to be rewritten as systems of lower order PDEs. Because sometimes that can help with a solution process. Okay. Any questions up to this point? Okay. Here are a bunch of examples of well-known PDEs, some of which you've seen, some you may not have. Okay. So here we have what's called a linear advection equation. Notice it has first derivatives with respect to t and x. Advection is a very important term when it comes to PDEs. A solution that exhibits propagation, for example, of a motion of a wave. Perhaps you have a wave that's moving from left to right, or possibly in both directions. So it's so equations that model that kind of behavior are advective in nature. By contrast, the heat equation models a very different physical effect, diffusion. You have heat energy diffusing throughout the spatial domain. So here we have ut is equal to uxx. So first derivatives, so when you have a first derivative with respect to time, like we have here, a first derivative with respect to x models advection. So whenever you see a term like that in your equation, then you know it's that kind of behavior that's being modeled. Okay. What happened here? Okay. Okay. Whereas if you see a second derivative term, that's going to describe diffusion. And in contrast to both, if you have a term that simply involves u, not a derivative of u, that's for a reaction term. So we actually have equations that include advection, diffusion, and reaction terms. That we have ux, uxx, and u. Here's an equation that combines both. So we have convection, also modeled by du dx, and then diffusion, that's uxx. But equations like this might also be called an advection diffusion equation. Actually, I'm going to move this example. It fits more closely with the others right above it. Okay. So here we have a very different sort of equation, Poisson's equation, that doesn't have a time element to it. So uxx is equal to some function f. That's in one space dimension. But if you're in any number of dimensions, then you'd have a Laplacian. So that can be written as gradient symbol squared of u, but it could also be written as delta u. So either way is acceptable for writing a Laplacian. Okay. And solution U refers to electrostatic potential. Okay. The wave equation I've not shown here. I think it might be further down on my. Oh yeah, it is further down the list. Can be decomposed into a system of two equations that have a form like this. I should mention. I mentioned this problem earlier, Berger's equation. This is an example of a quasi-linear equation. Now, an equation written in this form, where you have du dt, and then some function of u differentiated with respect to x, is what's called a conservation law. So that'd be ut plus some function of u, all differentiated with respect to x, equals 0. Now, if you actually carry out the differentiation of this with respect to x, first you differentiate with respect to u, and you get just plain old u, but then you have to multiply by du dx because you're actually differentiating with respect to x, and by the chain rule, you must include a ux. So that's what leads to this form here. So these two equations are saying the same thing. But Berger's equation is commonly written this way for solution purposes. And we can see here, because ux has a coefficient that depends on u, that's what makes it a quasi-linear equation. Here we have a semi-linear PDE. This part is we recognize from Poisson's equation, but now the right-hand side is not a function of just x, it's a function of u. So that's what makes it semi-linear. Here you've recognized a wave equation from other classes. UTT is UXX in its simplest form. But I could write it this way. Oops. If I were to carry out this matrix vector multiplication, I would have the first equation, du dt on the left side is equal to, if I carry this out, I get 0 times u x plus 1 times vx, so ut is vx. And then dv dt is equal to the second row of this, which would give me du dx. So what we have here is two linear advection equations, because you have first derivative with respect to t, first derivative with respect to x, just of different functions. But if I take this equation and I differentiate both sides with respect to t, I get this. But vx with respect to t is the same as vt with respect to x, so I can swap these. And now I fill in what vt is. Well, vt is equal to ux. So now I have uxx. So two different perspectives on the same PDE. That's either second order in this case, or a system of two first order equations. And because both equations depend on u and v, these equations are coupled together. They cannot be solved independently of each other. This one you probably haven't seen before. But
So I have a question.
Yes.
So in terms of solution numeric, which form is it?
Oh, I mean between this and this?
Yeah.
There's no hard, fast answer, but really what happens is that certain numerical methods might work better with one form versus the other. Okay, as an example, generally time-stepping methods for ODEs, like if I spatially discretize this PDE or this system PDEs, and that would give me ODEs, generally time-stepping methods for ODEs are meant to apply to equations that are first order in time. So therefore, this form would be more suitable. But there are also methods for solving a wave equation that work with this form directly. In fact, it even applies to my own methods, Krylov subspace spectral or KSS methods. I actually, in one of my recent papers, I had a wave equation much like this, only somewhat more complicated in terms of the coefficients. So to solve it, I used this form. But then a term was added to this PDE that involved a du dt, so first order derivative in time. And for that, what I needed to do was rewrite it in a form like this. So it just depends. A lot of times writing as a first order system is nice because there's so much theory when it comes to analytical numerical methods that applies to first order equations that it makes an analysis a lot easier. Other questions at this point? Okay, this equation, I'm not going to pronounce this right. Korteweg-de Vries equation. Too bad this is being recorded. This is a rather strange equation because what we can see here, it is it's not linear because we have this ux here. But what's interesting about this equation, unlike most nonlinear equations, it actually has an analytical solution. Nonlinear equations, and I'm talking about any of the kind of nonlinear, it doesn't matter if it's fully nonlinear or semi-linear or quasi-linear, any of those equations that are not linear can be incredibly difficult to solve. Like maybe there's no analytical solution known, but this one does have one, and the solutions are referred to as solitons, which is a certain kind of waveform. Because of a UX here, this is an equation that models advection. Here's a far nastier PDE, the incompressible Navier-Stokes equation. Oh, wait. Oh, that's right. Yeah, incompressible. Okay. So there's both compressible and incompressible. So here we just have the incompressible. Okay. So what we have here. So here we have this really system of PDEs, because you would refer to like a velocity vector of a fluid that would have three components for x, y, and z. And we can see that the PDE is nonlinear because we have a u here, and also from this gradient operator, derivatives, first partial derivatives of u here, all multiplied together. And then we have this condition that this is the divergence of u. So the fact that it's incompressible means that the divergence of u is 0. So this is what makes it called a differential algebraic system, because we have this so this condition included with there makes it a more difficult system of equations to solve. It's not just a differential equation; it's a DAE, differential algebraic equation. If it was simply compressible, then this condition wouldn't be here, and that makes a numerical solution more tractable. One of my recent PhD students, Brianna Bingham, her dissertation was about applying my KSS methods to the compressible Navier-Stokes equation. So Navier-Stokes equation is pretty much the most important equation in fluid dynamics. And there's like a prize offered of like $1 million to come up with an analytical solution of this equation, but no one has accomplished that. It's probably impossible. Another example of a system of PDEs, shallow water equations. So modeling movement of water, like modeling ripples, for instance, where h is the height of a water, and I believe u is a velocity. So here we have something with respect to t, derivative h with respect to t, and a function of h differentiated with respect to x. So this is conservation law form. So here we have two conservation laws that are coupled together. You may recall from previous PDE courses that the wave equation is a hyperbolic equation. So equations that model advection or convection tend to be hyperbolic. So that's what we have going on here. Okay. All right. And then we have a nonlinear equation, the iconal equation. So what's interesting about this equation is can be a measure of a distance within a domain. So whatever domain omega the PDE is defined on, the function on the right-hand side is 1 over wave speed. So then the solution, u, represents the arrival time at x, wherever you're evaluating the solution of a point on the boundary, like the minimum arrival time. And there's a very interesting numerical methods, like for example, one called the fast marching method for solving the equation. Now, in this class, we're going to be dealing with solving linear equations, but a lot of the methods that we'll see can be readily adapted to solve nonlinear equations. All right, so these are just some examples of PDEs. We'll spend a lot of time in the beginning of the class dealing with Poisson's equation, and then we'll deal with certain variations and also time-dependent equations like heat equation or wave equation later. Okay, so are there any questions up to this point? All right. So we're just getting our feet wet in shallow water. Now, what's interesting here is in terms of the schedule, this is what's meant to be covered for the entire week. Although this topic, well-posedness, is actually supposed to be, I need to fix that. That has to be moved up to this block. And you can see that's the next thing I'm going to cover. And I don't have a whole lot on that. And I have no more to cover for the week. So that could be a problem. Especially since we haven't got into homework just yet. So, and if there's going to be times here where I might have it planned to cover certain things, but then if y'all are having difficulty with the homework, then I'd rather spend time trying to address those issues, and that cuts into getting things covered. But I've sort of allowed for that in the schedule. Okay, so the thing is, if a very first homework problem, which is the only problem that doesn't feature MATLAB, I think it's not really possible to dive into that just yet. Not until I've covered some more things down here, unfortunately. So, so what I could certainly do is, obviously, we're about to end because there's only 5 minutes left anyway. So certainly this part on well-posedness is what I'll start with on Thursday. And what I'll probably just do is I could just, even though this is what's on tap for next week, I could just keep going, but obviously at a reasonable pace. So, since it's, I mean, I always like to say at the beginning of a semester, for students and teachers alike, it's the first day. No one's behind yet. Well, in many cases, it doesn't take as long for us to get behind. But now, it's first day. I'm already ahead. But don't worry, we'll fall back behind later. Okay, so what I'll do is I'm going to take these notes as I've updated them during class, and I'll post that on Canvas. And then this recording will also be posted on Canvas. Now, since I'm about to have, I have a half-hour break, then the class, then another class. I'm not sure exactly when that'll happen. I'll try to have everything up from classes, like each day's class, by that evening, like posted in Canvas or uploaded to YouTube or whatever. But we'll see how it actually goes. So, okay. Well, got through the first day anyway. Only one big flub up. Dang it. So, all right. Well, good luck with all you have going on, and I will, because I'm compelled to. I will, and yes, I'm kind of put off about that. I will be in Southern Hall 302 on Thursday, or whoever wants to make it there. Until then.
Thank you.
Yep.